To determine whether we should fit an arch model, we need to perform a test. So the test we're going to use is a Lagrange multiplier test for arch model or for arch effect. The test equation is given on the slide. Essentially, we're checking whether the square of ET is related with the past term, its own last lag term. Notice that it looks similar to the test equation we used before, but it's not the same because previously we only used ET and ET minus 1 in the test equation, but now it's ET squared. I also would like to remind you that the average value, the expected value of ET is 0, as we have already demonstrated in early part of this lecture. So this ET squared is essentially the variance of ET, because if you think about the equation to calculate variance, that's the variable itself minus its mean, then divided by sample size. So ET minus mean, which is 0, then divided by sample size takes square, but sample size constant, we can safely ignore it. So ET squared is the measurement of the bulk part of the variance. We're checking whether the variance of residual is related to its lagged term. So this is the test equation. If we have this type of a relationship, we identify an arch effect in our time series. And then we need to estimate an arch model accordingly. So to verify that condition, we need to test the hypothesis of gamma 1 equals 0. So we check whether this term is significant or not. The example that we use is a stock. The share of is the price of stock share is from Brighton Your Day Lighting Company. It's a makeup name, but we have the time series generated over here, and you may notice that obviously there's some volatility clustering effect over here around that region, but the pattern isn't that clear. We would like to use a test to give us a specific answer. What we can do is to first of all run the regression model first. Then we obtain the residual term, the residual series from the regression. Then we run this test equation. The dependent variable is the square of the estimated residual. And then we use the lag term in the regression model. R squared from this regression is 0.124, and the test statistics is 8.409. The t statistics itself suggests a significant first-order correlation already. From LM test, the test statistics is 62.16. It depends on the number of lag and R squared and the number of observation from the regression. Then we have the test statistic that's significantly above the critical value, which is 3.841. So we reject the null hypothesis and conclude that we identified arch effect or arch 1 effect. This is the arch 1 model, by the way, because we only include 1 period lag term in the regression model. In practice, it's possible to test higher lags, and it is you can leave it to the software. Once we identified an arch effect in the residual series, we need to estimate an arch model. The technique is called maximum likelihood method. My advice is to leave it to the software. So any reasonably good statistical software can estimate this type of model quite efficiently. So if we use exactly the same set of data, we can estimate the model. So this is the return from Stata. Later, I'm going to demonstrate how to obtain this set of output by using Stata. So the return is estimated to be 1.063, which means the return is fairly stable. It's about 1% or so. And you do observe some fluctuation that comes from the variance in the error term, the shocks. And that the variance of the error term is estimated by using this equation. So that's 0.642 is positive. And the coefficient of ET minus 1 square is also positive and is less than 1. The test statistics is significant as well. So that tells us the variance of our error term depends on the past value of residuals. So to make forecasting, the error term and volatilities are calculated as follows. The mean is easy. For the next term, it will be the same because we assume that the mean is constant. And for the error term, we simply use exactly the same equation over here, but we do need to find what the value of ET square, the ET hat square is. So that's how we can make the calculation. That basically we use the value of RT and the value of 1.063. That's the estimated value of RT plus 1 hat or beta null hat. Then using this equation, once we know the value of RT, which is available from our data set, that will give us the estimated value of HT plus 1 hat as well. So that's how to make forecasting. If we carry out this forecasting for every single data point that we have, we actually can estimate the time series of volatility as demonstrated on this diagram. So those are the values of HT hat at different point of time by using this equation. And we obtain this estimation from our ARCH model. And you may notice that the time varying volatility pattern is quite obvious, particularly over here. We have a large cluster of high volatility over this period of time, but at the beginning of our time period, the volatility is rather small. So that's the estimation based on our ARCH model, and this is a visual demonstration of volatility clustering and time varying volatility.